Okay, it's been requested that I do problem number 14, chapter 7. Let me go ahead and get to the book. Problem number 14, chapter 7. Alright. This is the one about a field experiment on the effects of perceived control. Residents on one floor of a nursing home were given opportunities for increased control in their lives. For example, arrange their own furniture, decide how to spend free time, choose and take care of a plant, whereas the residents of another floor were treated as usual. That is, the staff took care of these details. The feelings of well-being on a 21-point scale follow for the conditions of increased and no increased control. Using these data, test the null hypothesis that this minimal manipulation of perception of control had no effect on the residents' feelings of well-being. Okay, so we are testing the hypothesis that both floors basically have the same feeling. So the group that had increased control, their scores were 15, 17, 14, 11, and 13. And the ones that had no increased control, the other floor, were 8, 7, 9, 12, and 14. And what we're going to do is we're going to test the null hypothesis that this group had no effect on the residents. So we want to try to prove that these two scores, if there's any difference in them, it's just strictly because of sampling error. So the very first thing that you want to do for problem number 14, I like to go ahead and write out what I'm looking for. I want to know that the first mean is equal to the second mean. Okay, that's what I'm testing here. All right. Very first thing that you want to do, I want to go ahead and know how many n, figure out what my n is. I got 1, 2, 3, 4, 5. So I know that n is equal to 5 in the first group. Let me put this. Is equal to 5 for both groups. All right, I'm going to need an x bar for both groups. To calculate x bar, I'm going to add 15 plus 17 plus 14 plus 11. This is all repeat, so I'm going to go ahead and just give you the answers to these rather than calculating them out. So my first x bar is going to be equal to, on average, 14. My next x bar is just equal to 10. All right? And that's averaging out 8, 7, 9, 12, and 14 and dividing that by 10. All right? I'm going to have a standard error for each of them, correct? So my first group, I went ahead and calculated that out. Is equal to my variance. Never had to calculate variance. That's the 1 squared, which is the sum of the x squareds minus things divided by n. I'm going to get 4 for the first group, and I get 6.8 for the second group. So I know that the first group, on average, got a rating of about 14 with a standard deviation of 4. The second group, on average, got a score of 10 with a standard deviation of 6.8. All right. So after you find the mean and the standard deviation for each group, you want to go ahead to find the standard error of the difference between the means, and that's just that long formula. And so that we don't have rounding errors, let me do like this. That is n sub 1, which is 5, times the standard deviation, which I know here is 4. All right, and mind you, I already had it here, so I didn't have, I got it to equal 4, so I didn't actually have to take the square root of it or square it, times 5 plus 5 over 25. That's my second term. Oh, you know what, and I also missed a term here, so this is going to be, well, let me scratch this out. This is 5 times 4 plus 5 times 6.8. All of that over 5 plus 5 minus 2, which is equal to 8, times the term 5 plus 5, which is 10 over 25. All right. Go ahead and work some magic here. I know I'm going to have the square root of 20 plus 5 times 6.8. Hold 1 second. 5 times 6.8 is equal to 34 over 8 times 10 over 25. Go ahead and let me do the math out real quick. I'm going to have 34 plus 20 divided by 8 is going to be equal to the square root of 6.75 and 10 divided by 25 is equal to 0.4. So 6.75 times 0.4, 2.7. So I've got the square root of 2.7, which is just equal to 1.64. This number right here is going to be used when you actually compute your t-ratio. You don't use it for anything else. I think a lot of you are getting confused and assuming that is your answer, your t-value. It's not. Basically, all you've done is found the standard error of the difference between the means. Basically, you are just figuring out and trying to explain away any difference due to the standard error. Okay, so the next part you want to do is compute the t-ratio. This is when you'll actually use the standard of the error of the means, right? You'll take the difference between the two means. And so my means are 14 and 10. So I'll have 14 minus 10 over my standard error of the means, which is 1.64. All right, let me go ahead and do the math out on this. So it's just equal to 4 divided by 1.64. 4 divided by 1.64. My obtained t is 2.43. All right, this is my obtained t. All right, that doesn't really tell me anything. I need to know what's my level of significance. What number am I looking for? And I need to actually pick out my rejection regions. So if you go ahead here and draw your normal distribution, I'll go ahead and show you that. All right, first thing I need to know is I need to know what my degrees of freedom are and what my alpha is. When they don't give you an alpha, always assume a 95% alpha, 95% confidence interval, which is a 0.05 alpha. All right, so we are looking for the 2 points here that make up our rejection region. And all we want to know then is, does this 2.43 fall within our rejection region or inside of the gray area, which means that we need to reject the null hypothesis. All right. We're going to get that clear up. All right, let me go to the back of the book. Now, the table that you're going to be using here, I'm going to go to C. All right, table. This is chapter 6, problem number 14. Actually, I don't need to look this up yet, do I? All right. All right, you go to your critical values of t-table. Make sure this, can you see this? All right, and the way to read this table, table C, critical values of t, you need to know the level of significance, which if it's not given, always assume an alpha equal to 0.05. And that just means that basically when we have a 95% confidence interval, that we're pretty much sure that 95 out of 100 times our answer is going to fall within that region. And you have to know what your degrees of freedom are. In my example here, it was 8. So you go down the column to degrees of freedom. And if you go down and let's say here the numbers are in order, however they start to kind of jump right around 30, 40, 60. If, for example, I had degrees of freedom of 45, you want to go to the lower one that you have. Okay, you'd rather err on the side of safety. Same thing, 30, 60. And as you noticed, if you get, the higher your degrees of freedom goes, meaning the higher n is, the closer it starts to resemble the actual z-table, a normal distribution. So you can either use this bottom row here, or you could just use the z-table. The bottom row, degrees of freedom equals infinity, are also equal to the critical values for z. Right? But unfortunately, we've got like a really low degrees of freedom. So we're going to go here, go across towards 0.05 here. So that way, because of that, we know that 2.306 are our cutoff, okay? 2.306 is our cutoff. And this would be negative 2.306. All right, what was our actual critical value? All right, it's 2.43. All right, so now we need to figure out, is 2.43, where does it lie on our normal distribution? 2.43, our obtained t, falls here, right about here. This is in the area of reject. So basically on this one, we would reject the null hypothesis, meaning that there actually is some sort of relationship between someone's score on this exam and if they were on the floor where they were able to make decisions on their own, or if they were on the floor where other people did something. So that's based on this, we would reject the null, say that there actually is some sort of relationship. Now let's assume instead of doing alpha equal to 0.05, what if I had used something different? Like let's say I wanted to be more stringent. Let's say I want to be 99% sure. So let's say I did 99%. All right. That means if you think about it, my level of significance is going to go down. It's not going to be as great as 0.05. Here my level of significance is going to go down to 0.01. Does that make sense? Because I'm basically 100% minus 99% is equal to 1%. This 0.01 is essentially the same thing as 1%. All right, so if I drew this out again, and I'm doing a 99% with an alpha of 0.01, I go back to my table, I go to my degrees of freedom of 8, and I'm going to go across to where I find 0.01. Here is 3.355. Can you see that? 3.355, all right? 3.355, negative 3.355. Okay, a lot of you are also confusing this. This is a 95% confidence interval. This is a 99% confidence interval. I have increased my certainty, right? I've gone from 95, here I'm 95% right, or think I'm right. Here I'm 99% right, but basically what I've done in order to get more certainty, I've basically, if you look at this, because my error, I'm now at 3.3, I've basically widened my belt. Here, I was only 95% confident, but I could be more precise. Here, I basically had to loosen my reins, my limits, and I'm not as precise as I was before. However, I did gain confidence. Make sense? I'm now 99% confident, but that's only because now I'm saying, okay, the number is somewhere in between negative 3.3 and positive 3.3. All right? Now, my obtained t-value, 2.43, does not change, okay? Your alpha can change, but your 2.43 will not be affected by whether you're doing an alpha of 0.05 or an alpha of 0.01. So here, the 2.43 would fall right here. All right, this is not in my reject, and so I call it fail to reject. Fail to reject the null hypothesis. Okay, and this means that I would say that basically the two are the same, as opposed to the previous one where I rejected the null hypothesis. All right, thanks.